Welcome to Lesson 5.1, Solving Systems of Linear Equations by Graphing. This lesson is actually very similar to the lesson that we just did, Solving Systems of Inequalities. The major difference is that before, we were dealing with inequalities, meaning less than or greater than signs. Now we're going to be dealing with equations, which means equal signs. Our essential question for this lesson is how can you solve a system of linear equations? In order to answer this question, we're going to be learning two major skills. These are what I'm going to be calling our learning objectives. So our first learning objective is here, check solutions of systems of linear equations. Our second learning objective is going to be solve systems of linear equations by graphing. Before we jump into learning the skills, I want to go over two definitions. The first is systems of linear equations. A system of linear equations is a set of two or more linear equations written in the same variable. This part here, written in the same variables, all that means is that whatever two variables are present in the first equation, those same variables will be present in the second equation. So if you see x and y in the first equation, you're going to see x and y in the second equation as well. An example of a system is something like y equals negative x plus 8. And y equals 3x. So we're being given more than one equation at a time. That's what's making it a system. And again, because I see x and y here in the first equation, I also see x and y in the second equation. My second definition is solutions of a system of linear equations. And those are ordered pairs that are solutions of each equation in the system, meaning it satisfies all equations in the system, not just one. But again, my solutions are going to be written as ordered pairs x comma y. So for example, I might have something that looks like 2 comma 6. This is actually a solution to this system right here above. But how would you really know that? Well, that's what our first skill is, checking solutions of systems of linear equations. So learning objective 1. For example 1, our directions read, tell whether the ordered pair is a solution of the system of linear equations. So looking at A, I'm given the ordered pair 2 comma 5, and I'm given the system with the equations x plus y equals 7 and 2x minus 3y equals negative 11. The first thing that I want to do is determine what my x and my y values are. Remember, every ordered pair is written as x comma y. So when I want to determine what my x and y values are, I'm going to look at this first number here for my x, which is 2. And then I'm going to look at my second number here for my y, which is 5. So my x is equal to 2, my y is equal to 5. From here, I want to plug these x and y values into each equation separately. So working with equation 1, x plus y equals 7, I'm going to go ahead and I'm going to plug in x and y. Instead of x, I'm taking the 2 from the ordered pair. I'm going to keep my plus sign. And instead of y, I'm plugging in 5 from the ordered pair. And then keeping the rest of my equation, which is equals 7. If I go ahead and do this addition, I do see that 2 plus 5 equals 7. And 7 equals 7 makes perfect sense. So this is what I would call a true statement. And now my first equation is done. I'm going to move on to my second equation, which is 2x minus 3y equals negative 11. I'm going to keep everything the same in this equation except for my x and y. I'm going to plug in 2 and 5 where they go into the equation. So I'm going to keep this 2, but instead of x, I'm going to plug in 2 from the equation. Not from the equation, from the ordered pair. I'm going to keep my minus 3, but instead of y, I'm going to plug in 5 for my ordered pair. And then I'm going to keep the rest of my equation, which is equals negative 11. If I go ahead and work through this math, 2 times 2 does equal 4, minus 3 times 5, 15, and I'll set that to negative 11 and see if it's true. Well, 4 minus 15 does equal negative 11, and negative 11 equals negative 11 is another true statement. So since I have two true statements, one for each equation, my final answer is going to be the statement 2, 5 is a solution to the system. Okay. Keep in mind 2, 5 is not the only solution to the system. It just is one of them. And just like we had statements for systems of inequalities, our answers for systems of equations are also going to be statements. So you do need this full sentence here. And that's it. That's example A. Moving on to example B, you're going to see that we're going to follow the exact same process. So here our ordered pair is -2, 0. Our equations are y equals -2x minus 4 and y equals x plus 4. So looking at my ordered pair, my x is this first number, -2, and my y is this second number, which is y equals 0. And now working with each equation one by one, I'm going to figure out if this ordered pair is a solution. So I'm looking at y equals -2x minus 4 first. Instead of y, I'm going to plug in 0 for my ordered pair. Keep the equals -2. Instead of x, I'm going to plug in -2 from the ordered pair, and then tack on that -4. 0 stays 0 on the left-hand side. -2 times -2 gives me a +4, and then I keep that -4 from the end. 0 stays the same on the left. 4 minus 4 equals 0, and look, I have another true statement. I can't stop there though. I have to keep going and move on to my second equation. So I'm looking now at y equals x plus 4. Instead of y, I'm going to plug in my 0 for my ordered pair. Keep my equal to sign. Instead of x, I want to plug in -2 and then tack on the +4 here at the end. 0 stays the same on the left. -2 plus 4 gives me a +2, but 0 does not equal 2. That is untrue. So, since I have one true and one untrue, what does that mean? My statement or my answer is going to be that -2, 0 is not a solution to the system. Remember, okay, that the ordered pair has to satisfy all of the equations in the system. It can't just satisfy one, it must satisfy all of them. So even though you get true for the first, that doesn't mean that you're going to get true for the second. You have to check everything. Aside from plugging in, being given an ordered pair and plugging in, we can also check solutions with a table. So here we're given a system y equals x and y equals -3x plus 8. I have those two in my table right here in these two columns. However, instead of an ordered pair, I'm given a set of 4 different x values that I have to plug in for x into each equation and see what happens with the y values. So when x equals -1, for my first equation, I see that y equals -1. For my second equation, y equals -3 times -1 plus 8. That's equal to +3 plus 8, which is equal to 11. Okay, when x equals 0, y equals plugging in 0 for x, y equals 0. For the second equation, y equals -3, plug in 0 for x, plus 8. That gives me just the 8 because the -3 times 0 cancels out. Okay, when x equals 1, I get y equals 1 here. For my second equation, I get y equals -3 times 1 plus 8. Which gives me -3 plus 8, which gives me 5. And when x equals 2, y equals 2 for the first equation, and y equals -3 times 2 plus 8 for the second equation. That will simplify to -6 plus 8, which also gives me a 2. Now, by looking at a table, I know if something is a solution when one x value, meaning something from right here, gives me the same y values in both this column and this column. So I'm going to go through and check where the y's are the same. For the x equals -1, I get -1 and 11. Those are not the same. For x equals 0, y equals 0, and y equals 8. Those are not the same. When x equals 1, I get y equals 1 and y equals 5. Those are not the same. But for x equals 2, I get x equals 2 here, and y equals 2 here, and another y equals 2 here. So when I have one x value, okay, giving me the same y values, that's how I know that's how I know I have a solution. So again, my x was equal to 2, my y was equal to 2. So as an ordered pair, this is going to be 2, 2. And my statement would be that 2, 2 is a solution to the system. A little bit different from being given the ordered pair, but process-wise, it's kind of the same. I'm still plugging in x values into my equations, and then I'm just looking for where my y's turn out to be the same number. And that's that. We can now move on to learning objective number 2, solve systems of linear equations by graphing. So I'm being given two equations here, y equals -2x plus 5, and y equals 4x minus 1. Just like systems of inequalities, the first thing that I want to do is make sure that these equations are in slope-intercept form. And remember, slope-intercept form is y equals mx plus b. So I'm going to work with each equation one at a time, check that it's in slope-intercept form, and then go through the process of what I need to do in order to graph these guys. I'm going to write my equations at the top separately here, and then work with them one at a time. My first equation, y equals -2x plus 5, luckily is already in slope-intercept form, so I don't have to change it at all. I can go ahead and start to graph. In order to graph, I need two pieces of information. The first is my y-intercept. The second is my slope. So my y-intercept here is 5. My slope is -2, which remember, that's the same thing as -2 over 1. So I'm going to go 2 down and 1 to the right. Once I've gathered these two pieces of information, I can go to my graph and start to graph it. My y-intercept is 5, that's right there, and then I have to go down 2 over 1, down 2 over 1, down 2 over 1, and I'm going to continue to do this until I reach the edge of the graph on both sides. Once I have all my points, I'm going to connect them all. Don't forget your arrows at the end. And there's our first equation. There's the line for our first equation. Once I've graphed it, I can move on to my second equation, which is y equals 4x minus 1. Again, luckily, this is already in slope-intercept form, so I don't have to change it at all. I can go ahead, I can start looking for my y-intercept and my slope. My y-intercept here is -1. My slope is 4. Again, that's the same as 4 over 1, so I'm going 4 up, and I'm going 1 to the right. Now that I have this information, I can go to my graph, find -1 on my y-axis for my y-intercept, and from here go up 4 to the right 1, up 4 to the right 1, all the way on both sides until I reach the edge of my graph. Once I have all my points plotted, is that right? Yeah. I can go ahead and connect everything. Don't forget those arrows at the end. Now, with a graph, the way that I notice a solution is where the two lines intersect. And that's right there, circled in red. That point I can see is at 1, 3. I can check my solutions by plugging them back in the same way that we did during learning objective 2. And if I did that, I would see that they would produce two true statements. So my final answer would be 1, 3 is the solution to the system.